Alright, first thing I want to bring to your attention is the difference between a push vector and a pull vector. Okay? Anytime force is involved, force is going to be acted upon an object either in a pushing or a pulling manner. And life is better when it's a pull vector. Alright? You want pull vectors every time. So, whatever the object is being acted upon as, such as this being the object here, imagine that I'm behind this object here pushing with some force in that direction. Alright? That'd be the equivalent of me being down here pulling in this direction with the same force, right? So, if you have a push vector, simply push it along until the tail of the vector ends up at the origin going in the same direction. So whatever angle this is here, which is a 20-degree angle, will mirror it over here, like so. Right? So this is the pull vector, which is equivalent to this push vector right here. All right? Beyond that, the difficulty of these problems is getting the correct angle on your vector when you draw the problem. So the way you figure that out, once everything's a pull vector, step one, redraw all push vectors to pull vectors. Draw a coordinate system with the origin at the tail of the vectors. So whatever the force is acting upon. So if the force is here and you got something pulling it this way, something pulling it that way, the origin is right on that point. Alright? That puts the vectors themselves into quadrants, either the, if it's like this, first, second, third, fourth quadrants, right? The quadrants are what they always have been. If it's a slanted vector. If it doesn't slant, it's either going to be going straight to the right 0, straight up 90, straight left 180, or straight down 270. So if it's not slanted, it's right there in front of you. Once it's a pull vector, if it's going this way, it's magnitude 0, magnitude 90, magnitude 180, magnitude 270. All the slanted ones are going to be in some quadrant. Depending on the quadrant, in the first quadrant, theta we're looking for is going to be alpha. Ahead of myself there. Theta is going to equal alpha 2. Theta is going to equal 180 minus alpha 3. Theta is going to be 180 plus alpha. And 4. Theta is going to be 360 minus alpha. The same four relationships we've had before for the quadrants. Alpha is going to be the angle written in the picture. Okay, so make very clear to you, because this is what people mess up on in these problems. The angle in the picture is not always the angle in your problem. The angle in your problem is going to be theta, and the angle in your picture is going to be alpha. Depending on what quadrant you're in, it's going to change. So be careful of that. Write the vectors in r theta form, then add them like normal. Change them to rectangular form, add them up, change them back to polar form. So let's do a couple problems here so you can see how this works. First problem, two ropes are attached to a point and pulled on with directions of magnitude shown. What's the resultant force on the point? So, right here is where the force of the vectors is being directed. The point at the bottom of that pulley. Alright? This vector is the rope being pulled in this direction, here, 30 degrees above the x-axis. This vector is being pulled 45 degrees from the x-axis. Now, you can see here that I've already kind of superimposed a y-axis and x-axis over this point of force, right? So that establishes for us, for these vectors, if I were to draw them more clearly, there's one vector, right, going that way. There's my second vector going this way, right? Which quadrant is the blue vector in?
One.
It's in the first quadrant, right? And which quadrant is the red vector in?
Two.
The second. Now, let me, again, be very careful to explain this properly so there's no confusion here. 30 degrees is equal to the alpha for the blue vector. 45 degrees is equal to the alpha for the red vector. Okay? My goal is to find a magnitude and a theta, not an alpha. Alright, so be very careful here when we write these vectors out. So vector 1, in the first quadrant, theta is equal to alpha. So for vector 1, it's going to be 40 magnitude at an angle of 30 degrees. Because again, it's in the first quadrant. The angle theta and the angle alpha are the same in the first quadrant. For vector 2, theta is going to equal 180 minus alpha. So for vector 2, it's going to be 70 magnitude at an angle of 135 degrees. Again, specifically because it's in the second quadrant, I use the second quadrant rule. 180 minus alpha to find the angle. If I put 70 angle 45, the vector would look like this. That's 70, 45. It's going the wrong way. So again, 135 degrees is that direction. And keep in mind, if you just imagine straight up is 90 degrees, straight left is 180, the vector is between 90 and 180, the angle should be between 90 and 180. So it should be very obvious to you, if you understand this as well as you should, if you put the wrong angle there, it'll be going the wrong direction. Okay, so again, this is 0, 90, 180, 270, 360. So if it's in the first quadrant, it should be between 0 and 90, which it will be. In the second quadrant, between 90 and 180, it won't be, so you have to modify it. If it's in the third quadrant, it should be between 180 and 270, you'll have to modify it. The angle, the problem always gives you alpha, it never ever gives you theta. Alright? Once you write the correct vector addition problem, this is what it has been before. Vector addition is changing to component form. I want to make sure I'm in degrees. Right now I'm in radians, so I'm going to change to degrees. And then I'm going to type in 40 cosine of 30. I'm going to type in 40 sine 30. I'll type in 70 cosine 135 and 70 sine 135. Calculator holds all four numbers at once, so it's not that big a deal. So the cosine and sine of 30 get me the I and j for the blue vector. So 34.64i plus 20j. Red vector, I get negative 49.50i plus 49.50j. These are opposite signs, so I subtract 34.64 minus 49.50 comes out to negative 14.86. And these are the same sign I add, I get 69.50. That tells me the resultant force is going to be 14.86 to the left and 69.50 up force. So if I just ballpark that, it's kind of going to be like that. And imagine these forces working in that way. We're pulling really hard here, we're pulling a little bit this way, so it takes it back this way a little bit, but not as much as it would going that way, right? So it kind of seems to make sense if we kind of think of how all the forces are acting on this thing. Yes, it's going to be pulled in this direction, but not as far as it would have, because this is pulling it back this way a little bit. All right? Both forces are going up, which creates more force going up, but the horizontal forces are kind of acting against each other, so that kind of takes away a little bit of the force. All right? But again, that's our resultant vector. That's what it looks like. What we're looking for then is the magnitude and angle of that, right? So then we go to our three-step process here. Step 1, r is going to equal the square root of positive 14.86 squared plus positive 69.50 squared. We always put positives in this because when you square things you get positives anyway. You never use a negative in step 1. Type it in exactly like that. Square root 14.86 squared plus 69.5 squared in parentheses equals 71.07. Step 2. Alpha, reference angles, equal the inverse tangent of the absolute value, so everything positive again, the V over the J, 69.5 over 14.86. Again, only positive numbers in this step because of the absolute value bars. So inverse tangent, 69.5 divided by 14.86 equals, comes out to 77.93 degrees. Step 3, Theta is based on the quadrant. So if I'm going left and up puts me back in the second quadrant, right? So the resultant vector is in the second quadrant. So for step 3, theta is going to equal 180 minus alpha. That comes out to 102.07. About 12 degrees to the left of 90, right? Seems pretty reasonable based on the picture I drew. But again, 14.8670. It goes a lot more up than it goes over. So the correct answer to the problem is 71.07 at an angle of 102.07 degrees. If they did happen to give some unit of force, newtons, pounds, anything like that, you should put that on the magnitude. Like if it said 70 pounds, 40 pounds, this would be 71.07 pounds. They didn't give us any kind of unit of force here, so just leave it as a vector like that. That'll be sufficient. And I'm just going to say one more time, because this is where people mess up on these problems. The angle in the picture does not match the angle in the problem every time. If you're in the first quadrant, it does, otherwise it doesn't. The other place people mess up is both example problems I give you today have slanted vectors. Some of the homework problems have straight vectors, not slanted. Again, in vector world, 0 degrees, 270 degrees, 90 degrees, 180 degrees.
God bless you.
Any vector that's not slanted is going to be one of those 4 angles on it. It's going straight right at 0, straight up 90, straight left 180, straight down 270. Otherwise, it's slanted. It'll be in one of the quadrants. Alpha will be in the picture. Theta is what you're looking for. Okay. Every year, people see one of these in a problem. They all of a sudden don't know how to do it. I have no idea how to do it. I've never seen one like that ever before in my entire life. You never showed us anything like that ever, or said anything about it ever. That's usually exact words what they say. You never showed us this. You never talked about it. You never mentioned it could possibly happen. There it is.